Okay, so now we're going to take a closer look at this idea of a likelihood ratio for distinguishing between two classes, and particularly this first reading here on the 5-minute stats, the likelihood ratio simple models.html. So that's here. So this vignette here describes how to go about comparing two models using a likelihood ratio. And the two models, we're going to consider the very simplest case where the two models are what I'm going to call completely specified, which means there's no free parameters anywhere here. And so here, what I mean by model is it's going to be a probability of some observed data under a particular model or hypothesis. So the two different models will be, one will be his one distribution on potential observations under one model, and then a second model will be the probability of the different possible outcomes under a different model, and we're going to be trying to compare those two models. And here we have a motivating problem here. So the problem is I want to try and classify an elephant as either a forest elephant or a savanna elephant based on its DNA. So this problem comes from, it's a kind of a simplification of a real problem I worked on with Sam Wasser and other collaborators, where Interpol sees ivory from poached elephants. They've got ivory, they can get DNA from the ivory, and they want to know, essentially they want to know where in Africa the ivory came from based on its DNA. So this is a simplification of that problem. Let's just imagine we've got this DNA. We want to say, did it come from a forest elephant or a savanna elephant? And the forest elephants and the savanna elephants look slightly different from one another genetically. In fact, they look slightly different from one another phenotypically. So you can, if you know your elephants, you may be able to tell them apart just by looking at them. But we don't have the elephant in front of us, we just have its DNA. So, okay, so what's the data that we might use to try and answer that? Well, to try and simplify things, I'm going to assume that elephants are what's called haploid. That means they just have one copy of their genome. Actually, elephants, just like humans, have two copies of their genome, one that came from their mother and one that came from their father. But just to simplify things, I'm going to imagine they only have one copy of their genome. And then the data are going to consist of you go looking at their DNA at different positions along the genome. Those positions are going to be called markers. So at each marker, here I have 6 markers. At each marker, we're going to look at the DNA and we're going to see what type it is. And the types are called alleles. So I'm just going to assume that there are 2 types at each marker that I'm going to call 0 and 1. So here's a possible data set. Here, 6 markers. At the first marker, I see allele 1. At the second marker, I see allele 0, etc. So I'm going to try and decide what's the support from these data for the 2 different models. Is this a forest elephant or is it a savanna elephant? Okay, so to do that, I need models for forest, what data might look like for forest elephants and what data might look like for savanna elephants. So here's that information here. So the idea here is that at each marker, I have some external information on how common is each allele in the savanna elephants, that's FS, and how common is it in the forest elephants, that's FF here. So this table here, I'm assuming this is given to you or given to me, and that I know that, say, 40% of, at the marker 1, 40% of the savanna elephants will have allele 1, they'll be of type 1, whereas the forest elephants, 80% will be of type 1. And at marker 2, 12% of the savannas will be of type 1, whereas 20% of the forest will be of type 1, etc. So I assume that information is given. So now I'm going back to my data here. I'm asking, well, do these data support this elephant being from a forest elephant or a savanna elephant? And so I can build a simple model that assumes that these data are independent across the 6 markers. So looking at the data at marker 1, I see a 1 allele, and we know that the 1 is more common in the forest elephants. It's actually at 80% frequency rather than 40% frequency. So that seems to support the elephant possibly being a forest elephant. Then I look at marker 2 and I see the 0 allele. Well, I know that the 0 allele is more common in the savanna elephants because the 1 allele is less common at marker 2. So now that's beginning to support the savanna elephant model. And the idea is, how do I combine that information across these 6 markers where some alleles might support a forest origin, some alleles might support a savanna origin. So that's where modeling comes in. So the modeling assumption I'm going to make is that the data at the 6 markers are independent. And that if it came from a forest, from a savanna elephant, then they will come from these frequencies, whereas if it comes from a forest elephant, it would come from these frequencies. So here is, so X here is the data, and MS stands for the model that the elephant is a savanna elephant. And so the probability of the data X under the hypothesis or model, if you like, that it's a savanna elephant is given by the product over the markers. That's that product over J of F to the power X times 1 minus F to the power 1 minus X. So that's just a clever, if you like, a succinct way to write that it's, because X is either 0 or 1, that expression is F if X is 1, and it's 1 minus F if X is 0. So that's just a clever way to write F if X is 1 and 1 minus F if X is 0, every X is 0 or 1. So we can just product that over markers. That's a modeling assumption. And that's what I mean by a model here. It's a probability distribution on possible outcomes of our experiment. And then here, underneath that, P of X given MF, that's a second model. That's the probability of the observed data under the hypothesis that the tusk came from a forest elephant. And then the likelihood ratio is simply the ratio of these 2 probabilities. So you compute the probability of, well, actually, maybe I should say the likelihood for model M is just the probability of X under that model. And so then the likelihood ratio for 2 models is just the ratio of those 2 likelihoods. Okay, so maybe I can just show an example in code here. This code here would produce, would compute those 2 likelihoods L under the savanna frequencies and the forest frequencies for given data X. So these are using the numbers that we saw above and computing the likelihood ratio as just the ratio of those 2 likelihoods. And in this case, for these data and those allele frequency tables, that is for those models, we get a likelihood ratio of 1.8. Okay. So a couple of things here. Let me just say a couple of things. Firstly, I use the expression, I hope I use the expression likelihood for the model. Another term that I would be happy for you to use is the likelihood under the model. So, but probably best to talk about the likelihood for the model. What I would avoid saying is the likelihood of the model. And that's because likelihood here is being used in a technical sense, if you like. The likelihood for a model is the probability of the observed data under that model, P of X given M. Whereas in everyday speech, likelihood is often used as a synonym for probability. So if you say the likelihood of the model, you have this danger of misinterpreting it as the probability of the model, because likelihood and probability in everyday speech are often used interchangeably. But the likelihood of the model or for the model is not the probability of the model, it's the probability of the data. It's the probability of the data under the model. So because of that, I encourage you to use the terminology, the likelihood for the model, which means the probability of the data given the model. Okay, So as the first comment. The second comment is to ask, well, is 1.8 a big likelihood ratio or a small likelihood ratio? Obviously, it's bigger than 1, which means that these data are more probable under the savanna model than they are under the forest model, because we computed the ratio that way. So the ratio is bigger than 1, which means the data favor the tusk coming from a savanna elephant. But you could ask, well, how strong is that? How much do they favor? Is that a lot of strong evidence in favor, or not so much? And we'll come to more quantitative answers to that question later in the course. But for now, I just want to emphasize that likelihoods have a kind of a human scale to them, right? So this likelihood ratio is here, it's 2. Is that a lot bigger than 1? I think your gut should say it's not a lot bigger than 1. The data favor the model by a factor of like 1.8, 2 to 1 roughly. It's not that strong. It's not like 1,000 to 1, which you might think of as strong. And I think it's easy to kind of lose sight of this maybe slightly intuitive view, but it's really important, as well as learning a more quantitative way of thinking about these things, which we will look at later, to keep in mind this very kind of intuitive view. The likelihood ratios have a rather human scale to them. And I'm going to emphasize that the likelihoods themselves don't have that property, right? So the ratio has that property. But when we look at the likelihoods themselves, we'll see they don't really have a human scale to them. I'll come back to that point later. Okay, so just ending here with a trivial point, which is that we could have computed the likelihood ratio the other way, savanna versus forest instead of forest versus savanna, and we would have, of course, gotten the inverse. So if you get a likelihood ratio of, say, 1% for one model versus the other, then you would get a likelihood ratio of 100 to 1 if you reverse the question. And the other kind of point to know is that people will often work with the log likelihood ratios. And that just means they take the log of the likelihood ratio. And usually that logarithm in mathematicians usually work with a base E logarithm, although sometimes it can be, if you're trying to just keep the human interpretation of a likelihood ratio, it can sometimes be useful to give it in base 2 or base 10, which is a bit easier to do calculations in your head. For example, if I tell you that the log likelihood ratio is 3 base 10, then you can quickly tell me it's actually 1,000, which is kind of big. It's a bit harder if we use base E, but okay. So that's a minor point. And there's some exercises you can try and do here to test your understanding of these ideas.